Hello, testing. Okay, before we start, so can you let me know, what do you think you need to include inside your progress report? So we decide together what's the format we want. So what's the progress report? What's the thing you need to include in your progress report before you submit? Huh? What's the thing you need to include? What do you think is sensible to include here? Huh? Okay, so discussion, topic, or details, and then what else? Huh? Sorry? 听不到。日期时间，OK，so so 这个应该是叫做 meeting details 啊。So basically it's a date, time, venue 啊。OK，so to prove that when you meet 啊。What else do you think you need to include? 人呢？有没有人哦？Any people coming? Attendance, right? Okay. So you have to say who didn't come, why don't come, something like that. I don't know. So if got absentees, you need to tell like what's the reason. Anything else you think important? Huh? 下个目标? I mean, this one can be included here lah. So, um, planning, planning. Right. Oh, okay, okay. Yeah. Anything else? I think pretty much. Okay. Yeah, I think pretty much. Yeah. Sorry? Yeah, I think pretty much. Yeah. Yeah. So you need to prove that actually this meeting is happening, right? Okay. Yeah. Okay. So make sure you include these things. Okay. This is one thing. The other thing is we have a student council that can help uh, advertise our seminar. So we hope that this seminar can attract new people, right? So it's like maybe I would say junior, lah. Senior, I think not much already because they are pretty fixed. So hopefully the junior come and then they will get inspired then they can work in this area in future or attract more people, and then they can come and get this course in future, right? Okay. So, but we need your cooperation. Okay, we need your cooperation. Do you have uh, all the group leader here? Joel not here. Is Joel coming? Joel not here. Okay, so Joel group need to take note, huh? Maybe tell your group leader. So so few things we can do, we want to do. We can make it more like a seminar. So if you notice that our department, right? When we have talk, we have speaker details, right? And then abstract. But we're not gonna put your details, huh? Okay, I'm not gonna tell where you came from, huh? But 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 oh, he got template. But what we want from you was your maybe one of your photo, okay? Yeah, maybe recent photo, and then second one is 什么 have short hair, huh? Oh, okay. Recent photo, lah. No need formal one also can. And then second thing is your abstract. Okay, obviously your title all together. So title, abstract, and one of your photo. Okay, if you willing to share. If not, then people will see you as a name. That's it. So I want it by tonight because I need to pass them tomorrow. Okay, so the latest is tomorrow morning. You need to give to me. So I give you one night to prepare. Hmm? Okay, so let me write here. So everyone, please submit. Uh, passport size photo. But this passport size photo no need to be formal. You can crop from anywhere. 你搞怪了你也是可以的，随便的。It's just something that can represent you. Make sense? It's not only formal. It's not like criminal like that. No. Okay. So this one is a live photo lah. Okay. Something that can represent your identity. I mean your character, not your identity. We don't even care your identity. So okay. Second is your final topics. I think pretty much you need to finalize already. But if you really, really want to change at the last day, 请猜 you lah. But tonight you need to give me one topic. Okay. And then second thing is your abstract. Abstract no need to be long because you only 20 minutes. How much thing you need to say? I just say few lines, one line, two lines is enough. Okay. Yeah. Okay. So please submit to your leader by tonight. And then I will make a OneDrive and then I post into the team chat so that the leader can upload there. Okay, understand? Can understand? Get it? Clear? Okay, so I give you one night to prepare. Latest by tomorrow morning, you have to give me before noon. Okay, for the leader, before noon, you need to give me by tomorrow. Yeah. Then yes. You, well, I will give you a OneDrive link, and then all of you submit as a folder to me or zip up to you. A leader will help to collect all these. Okay. Okay. Yeah. So Joel is not here, so the group member please inform him. Okay. Um. Right. Okay. Huh? Yeah. Okay. I think that's it. Yeah. So there's something to share from yesterday. Yesterday seminar, right? So if you look at this problem here, especially the example here, what is this two thing? Can see or not? That two equation, what are they? Yeah, I don't mean that I want a variety out of that, but don't these two were defined like two set of zero set. Okay, so actually they are polynomial equation, right? So actually these are affine variety. Okay, if this k here live in C, huh? Oh, okay. So this partial here is says that it's just some non-zero x number. Yeah. And then it asks a question that let's say this k1, k2 is integer, let's say for prime. Okay. And then both zero, maybe 1, 0 can. And then solve simultaneously. Okay. But if you view them as variety, if you want to solve them simultaneously means what? These points live in the intersection. Okay, in the intersection. So this is a natural thing that think about. But why I want to share this is actually this product here being equals to one number actually is a group structure. When is it a group? Any number z1, z2 that satisfies this equation is the group structure. Okay, when is it a group structure? Actually, when this partial here equals to 1 is a group structure. So actually, it at the same time, it is a group. Okay, so they phrase this question into, if you look at this, the first curve you define here, the algebraic variety, so intersected with the coset of subgroup. So why is it coset? Because you not consider one, right? You consider different number, okay, different number in different number, different constant. Okay, so you view it as a subgroup because I think it's easy to prove that this form a normal subgroup because it is abelian. Okay, it's abelian, so that group will be a full subgroup of C E C2. Okay, so you can ask about the concept, and then the question will become for what K1 K2 does every concept of subgroup intersect up? Okay, yeah. So some very elementary uh, question about zero set. Okay, we can turn it into algebraic question. We can turn it into a group question. Okay, abstract algebra, right? And then the result, there's some of the result very interesting. So so if so, you can see that something is called rotten. Okay, rotten when it satisfies some dimension property. Okay, but this proposition says that something is rotten if and only if there exists some Zariski open dense set. Okay, so what does this mean here? So one side is dimension, very algebraic stuff. The other side is topology. Okay or not? Okay. So this is one of the instant that how algebra can link to topology. Okay. One side you just check topology character. One side you check algebraic characteristic. I mean, okay. Yeah. So later when we do Riemann rock, it's also similar idea. Okay, we can link algebraic characteristic to a topological characteristic. Okay. Okay. Make sense? Okay. So that's why this course is called algebraic geometry. So you link the geometry and algebraic together. Okay. But how to go from geometry to topology? Basically, is a continuous deformity. So when they have the same topology, they are the same thing. Okay. Okay. So this is what you use. I mean, what we use, not you use. We use. Okay. Algebraic geometry is very useful. Okay. Maybe it's not useful for you to cut your veg, cut your meat, buy meat or what, but there are people using these things. Okay. All right. Yeah. Anything you want to ask me or not before we start? I'll see how it goes. But target is to do Riemann rock. After Bezout, we'll do Riemann rock, and then we do amper divisor. And then afterwards, if we finish earlier, maybe we can do revision. Hopefully, the last lecture will be a revision. Then we won't have an extra revision class. Hmm. It really depends. But for this course, do you need a revision class? Do you think you think you need so? Because I don't know what's the content you want to discuss. Can you let me know what you want to discuss? Then I will decide if we're gonna have an extra one, or I just make it a last lecture. I mean, let me tell you honestly, mm, honestly, I'm gonna tell you is I want I will just tell you what topic will come up. That's it. Yeah. Because there's no how to say there's no past year, there's no like how to say um, there's no some standard question that I will gonna follow. Yeah. So you need to trust me that those questions are picked based on what we have learned. You have to trust me that. No. Those are your tutorial and assignment. Yeah, yeah, yeah. So because there's no past year, so there's nothing for me to give you and try and play. Uh, if you notice, even if I gave you past year, I won't just change number. If I gonna let you cheat, I will just give you the whole question. I won't like 骗你又骗我这样，要骗就骗好好的骗，对吧？I mean, I think you know what I meant. I mean, like, if I gonna give you mark, I will just give it to you. I think the easy question is enough for you to score. But this is what I hope for, lah, but I hope so. The easy question is enough for you to score. But there's something that maybe it's not, I don't think it's super hard, but definitely you need to understand what we did in the class. Yeah, because how to say, maybe, okay, I often got a comment that in my class, right, actually not enough examples. Let me tell you, sorry, because you know why you have this kind of okay, exactly. I want to explain why you have this kind of perception here. Because you don't understand enough the concept. So you think that the example is not enough. Because not enough for you to make inference. You get what I mean? Not enough for you to draw some conclusion that you want to make. Okay, this has this has advantage and disadvantage. Disadvantage is it could be the conclusion that you want to draw is wrong actually. You want just to want to prove to yourself that this is true. But what I want to say is example is never enough. Actually, never enough. Never enough. It's never enough. Okay, so I'll try my best to give examples, but Uh, but if I don't give, then maybe you need to think about it. Actually, this is real life, you know. This is real life. When people talk to you, it's a very abstract one, you know. They don't straight away tell you what they think inside their mind one. They will tell you bunch of irrelevant, like irrelevant stuff. So I think this is one of the skill you need to guess what people say. Mm, yeah. Mm, yeah. It's never enough, lah, I think. Yeah, never enough. I give you 10 also not enough. So I guess you need to read more, I think. I also read a lot. You have to read a lot also. That's why I will give you a lot of reference actually. Yeah. So you have to read. You cannot just rely on one thing. You cannot just rely on my lecture note or what. You need to think of my lecture note as a, how to say, as a guide, as a um, supplementary material, okay, to your textbook. Okay. I wouldn't say that the lecture note is complete, but it should be a supplementary. So that you read this lecture tutorial part, sorry, the textbook, you don't understand. Hopefully, I will let you understand like through my explanation, or I fix something inside the textbook. Yeah. Does it make sense or not? Does it make sense? Yeah. Okay or not? Yeah. I think all of you have reached to a stage that not everything you read you understand. But this is the natural state. This is the natural state. This is natural. OK， 华语的意思说，这才是你应该要经历的东西。Not just about maths. Already tell you, life is also like that. Life is also like that. 你可以补习吗？哎，补习叫我怎样做老公，叫我怎样做老婆，我要去补习，我要花钱补习，叫我做老公。Got 啊，got this kind of thing 啊，got course 啊，got the psychology class right? Got. 啊，你可以补多少个东西？我问你，How many thing you can go tuition？你要补完全部东西？So one thing I want to challenge you, actually, you also have to challenge yourself is dare to make mistake. Dare to make mistake. 你 if you don't get A in this class is fine, you know. But if you don't get A, maybe somewhere else is not very fine, you know. You understand what I said? You don't understand what I said, huh? But try and remember what I said. Maybe one day you can think about it. You don't get A here is a very fine one. But after school, you don't get A, then and that's it. That's it. 真的 it's like that. Your boss won't give you second chance. Your husband won't give you second chance. Your wife won't give you second chance. Your mother won't give you second chance. Your father won't give you second chance. Huh? What do you think? I, I mean, for example, deadline. Deadline. I give you an example. Deadline. What is deadline? Why is it called deadline? Something like that. The line is that. Huh? No. I give you another scenario. Let's say lah, choi lah, but your father have to die tomorrow. I cannot go back. Can I ask for extension? Can I extend your deadline? If he gonna walk away, then he walk away already. You try and extend. Go and pray your God. Pray to your God. See if you can extend or not. Pray to the black and white. Who knows the black and white one? Okay, maybe it's not Chinese, then you don't know. 黑白无常. Some angel that gonna bring your father away. And there's no second chance one actually. Real life, there's no second chance actually. Okay, yeah. Hey, tell you the story about my grandma again. I told you that she's died, right? She's dead, right? But before she dead, 1 week before she is dead. Um, yeah, 1 week before she's dead. Hey, you still remember I go for how many days? Holiday that day. I mean, go for you remember or not? I think when I teach you guys, right? You don't remember. I think I take leave for few days, 3 to 4 days, I think. But I missed their class once only, 3 to 4 days. My grandma is pretty sick already, actually. My parents are back already. So when she almost want to pass away, they asked me to go back. And then 1 week before she died, she can still wake up, speak a little bit, but it's just speaking to herself. But from their description, it's like maybe she's speaking with non-human already. You understand what I say? Maybe you can, I mean, there's spirit there, they can speak with them. But anyway, so she asked my uncle. My uncle is the one that that live with her all the time. She asked my uncle, when's your big brother is going to come back? The big brother is my another uncle, the oldest uncle, 大伯. My big uncle was living in Brunei, and then we stay in Cebu. So there's some distance, but not too far, but there's some distance. But this star boy is like, can I ask for extension? Kind of attitude. Why your mother die now, you cannot come back now? Why you need to wait until next week to come back? Can you imagine what happened to my grandma? She's not dead yet, but she cannot talk anymore. She just lie on the bed. Cannot open eyes already, I think. It's like 植物人讲 It's like coma. You can think about coma. 植物人. I mean, like, how to say, cannot wake up anymore. It's just like, only got breath only. Coma, okay, yeah. Coma, okay. Coma, okay. 昏迷. Okay, yeah, coma. So for for 1 week it's like that. Oh, for the whole week it's like that. Then after my big uncle come back on Friday, he finally saw his mother, but his mother cannot talk with him anymore. If he come back one week earlier, he can still talk with him one, but it's too late. Then only then my grandma passed away on Sunday. So do you think that my grandma is waiting for my uncle? Is he granting his son an extension? I think it's pretty sad, I guess. This is a real deadline. Deadline. Serious deadline. But anyway, yeah. So this is the story about deadline. Okay. Yeah. So we'll continue. We'll try to prove Bezout's theorem. So yesterday we proved that every principal divisor has degree 0, and then today we're going to use that. Okay. Before that, lecture. So before that, we'll talk about this Jacobian variety. Okay, so what's a Jacobian variety? So since every principal divisor has a degree 0, we can actually induce a homomorphism. So this degree function will induce a homomorphism. From CLC to Z. Okay. So degree is a map to Z, right? Because we just add up all the multiplicity. And then since we send all the principal divisor to 0, then this induces a homomorphism here. Okay, because we say that D is equivalent to 0 if it is a principal divisor. And then at the same time, this principal divisor should have degree 0 also evaluate to 0. Okay, so D evaluate to 0, D evaluate to 0, and then the principal divisor also evaluate to 0. So they all evaluate to 0. Okay, so the whole equivalent class we send it to 0. Then what we're going to define is the Jacobian variety. So since we say that it's a variety, right? So it must be a closed set. Okay, so we define it by Jack 0, then which is sometimes they say CL0, okay, which is all the divisor in the divisor group such that the degree D is 0. Okay. Okay, so there's some remark here. So I mean, for those who know a little bit of homological algebra, right? So we can rephrase this into this form here. So actually there is a short essay sequence. Okay, looking like this. For those who don't know, no need to worry too much about it. So basically what this short essay sequence says is basically for every map you have here, right? The image of a map is equal to the kernel of the previous match. Right? Okay, wrong. So the kernel of the match is equal to the image the previous match. Okay, so basically you map into the kernel of the next map. Okay, so think about it, is it correct or not? So what is CL0 into CLC? So basically this is just the inclusion. Okay, and then the other map I told you already, right? This is a degree map. Okay, and then the other two map, 0 go into something is just also inclusion. Just 0 go into it. And then Z to 0, everything sent to 0. Okay. So kernel of the degree, is it this thing or not? Just now we define, right? So kernel of this degree map is the image of this inclusion here. And then think about this. What does this mean? Kernel of this 0 map here is the image of degree. Meaning what? What is the kernel of 0? Everything, right? Everything. So is subjective. So this map have to be subjective. Good. Yeah, so I think this is what we yesterday. This map is subjective. Okay. I mean, basically, you just give you one number, you write me one divisor that can to it. They have zero or something like that. How about this? Kernel of this inclusion is equals to the image of this. What's the image of this? What's the image of this map? Zero map to where? Zero. So kernel equal to zero means what? This map is ejecting. So this is how useful on this short essay sequence. We will do more in algebraic topology if you come. Okay. Okay. Yeah. Another remark I don't want to make. Basically, is this variety here pretty much will determine what your curve is. Okay. So different curve will have different Jacobian variety here. Okay. Next, before we go to Bezout theorem, so one proposition we can prove here is the Jacobian variety is trivial if and only if C is rational, or actually C is isomorphic to P1. Okay, or actually birational in this case, birational. The isomorphism here is birational. Okay, so yeah, should we prove this? Okay, one direction we already proved. Which direction we already proved? Huh? Right to left. Right to left. Okay, so why is it right to left already proven? If it is isomorphic to P1, yesterday we compute about CLP1, right? But what's that? Z, right? It's isomorphic to Z. So the image is Z. So what's the kernel? Zero. Okay, so meaning this kernel is a trivial. Okay, so one direction we already proved. As you know that CLP1. Okay. Isomorphic to Z, right? Okay. How about the other direction? Okay, then we suppose then CLC is 0. Okay, but CLC is 0 means what? CLC 0 means what? What's the definition here? So there's nothing degree 0. Is what we should say here. The degree 0 divisor is only equal 0. Okay. In other words, so then any two divisor D and D prime of the same degree, then you can look at the difference, right? Okay. But their difference is by a principal divisor, because degree of principal divisor is always 0. Okay, so this means that actually these two divisor is linearly equivalent. This is about like showing kernel is 0, and then showing that fx equals to fy implies that x equal to y is the same. Okay. Okay. All right. In this case, let's let P not equals to Q be two distinct points on C. Okay. And then on C, right, we know that 2 points is always linearly equivalent to each other, because you can simply write down the how to say write down the write down the function. Okay, write down the function that realize this. Okay, do you know how to write down this function to realize this rational function to give, let's say, the divisor of f to be p minus q? Do you know how to write down this function here? Two divisor to be equivalence is their difference equal to some principal divisor, right? Okay, so do you know how to write down this f? Let's say on the pq, s minus p over s minus q. Yeah, that's it. Okay, so you need to make your p as a 0 and then make your q to be a 4. Okay, s minus p, s minus q. Because our space is a projective space, so it's pretty easy to construct. Maybe different case, maybe not. Okay. So in particular here, the rational map that we have here is a regular map. Okay, it's a regular map. Okay, such that we know that, so such that actually the pre-image of 0 is P, and then the pre-image of infinity is Q. Okay. Don't be confused why I say these are the pre-image, because it is actually a pullback. It works like a pre-image. Okay. So yesterday we say that the degree of f is pretty much determined by the degree of this pullback, right? Okay. So how many pre-image are under 0? Well, actually there's 1. So since f has degree 1, this f will is meaning is injective. Okay, so meaning is injective because only one thing inside the pre-image. Injective. Okay, so that this injective map, rational map here, will induce us a map on the function field. Okay. Okay or not? Will induce isomorphism on function field. How to induce? The function field will go backward. Okay, going backward. Which means what? So going backward, right? Injective map will induce a surjective map going backward. Okay. But you are surjective field homomorphism. So meaning what? You are also an injective map. Okay, so this means that you have an isomorphism of function field. Okay, but if your two function field are isomorphic, meaning what? Meaning by the equivalence, f is actually an isomorphism between variety. Okay, it's birational equivalence here. Make sense? Okay, so this is a one thing I want you to remember about categorical equivalence is you have one birational equivalence implies you have a isomorphism in the variety. Okay, this is true in the affine case also. Okay, make sense? Okay. Right. Yeah, I think this is the whole thing, everything I want to talk about Jacobian variety here. Okay, so let's do a little bit set up for Bezout theorem before we take a break. So the next part will be focusing on Bezout theorem. Okay, so to do a Bezout theorem, actually we're gonna just focus on curve here. So a plane curve is one-dimensional projective variety. I guess I have to put this before and but we do the order a little bit different from the one in the book. So what's this plane curve here? Basically, we just consider points in P2. So actually, it's a hypersurface in P2. Okay, but since this is a P2, then it will become a plane curve. Okay, such that this F here is a non-zero homogeneous polynomial of degree D. Okay, yeah. KD is the degree D part, right? Yeah. So we view this ring as a graded ring, and then we have the degree D part. Yeah, yeah, yeah. But if you want to remove this also can, because I already write out in Word. But if you don't see the word, you see from this symbol also should know that it's a degree D homogeneous. Huh? Oh, there's a subtlety here, right? Top and bottom, there's a subtlety. Inside, I mean, at least the notation used in clause and my thing. Because there's one of them includes zero, one of them doesn't include zero. You can go and notice. It's a little different. Yeah. So one of it is no zero inside there. One of it is got zero inside. Mean, yeah. Yeah. There's some subtlety, but I forgot which one is which. But anyway. Okay, but I think this one is non-zero, but I guess because here non-zero. Yes. So here there's one thing that just now when Chuan asked me about. So basically, two curves, C and C prime, with defining a function f and f prime. Okay, so let's write down because I need this f. Are projectively equivalent if there's this a map A from GL3, okay, such that A star on this function f is equal to f. I do the other way along. See, I guess this A, this A should do the other way around, right? Because for the A star. A is a map of variety, and then you induce a map on. I think because f is a function, right? So you will induce map. So if you have if you have map on variety, you will induce a map on function. Yeah, go back. Yeah, exactly. Okay, so why we only look at the GL and GL3 here? Because an element of GL3 will bring lines through origin to lines through origin. Okay, yeah. So that's why we only consider up to GL3. And then there's a lemma which we not gonna prove here, but I think it's a very interesting to look at. Is if you have a C, which is a plane of cubic curve, which decomposes into three lines, there's really only few ways you can draw it. Okay, what do you think? What do you think? You got three lines. What could happen to these three lines? What do you think? A generic one maybe is something like these are correct or not? Generic. Okay, what could happen? What else could happen? 莉迪亚要不要 try 一下？三条线可以怎么玩？啊？ two parallel. Okay, sure. So two parallel, and then one of them cut through it. 不等于 anything else? Three parallel, yeah, sure. Three parallel. And then still got one more. Huh? Still got one. What else could happen? The three intersection point also can be degenerate. So the claim is these are the possibility that you will get after you're doing project. You use this consider up to projectively equal things. Okay, so let me write down the form here. So the first one is actually you can write it as x0, x1, 0, x1, 0. And then let me see. So the second one, I'm not sure whether I'm pairing these polynomial right or not. Let me write down first. Can you check whether I'm pairing them right or not? Does it give the variety that you mentioned? Okay, I think I'm right. Okay, so you can try and think about this. Okay, so you can see some intersection here. So we will define the intersection multiplicity, okay, of C and C prime at a point P. It's a very algebraic definition here. I'm not going go and count the curve, the intersection number inside the set, but it's gonna define by this dimension of the local ring, okay? Quotient, okay? Quotient by what? Quotient by the ideal generated by F and G. Okay, so F and G here is the one that generate C and C prime. C and C prime. Okay, so one lemma here, obviously, we need to link it back to the set of intersection. So how do we know that there's something lying inside the intersection using this number here? So our first lemma we're going to prove is if this IP here is greater or equals to 1, obviously have to be positive, right? Non-negative, I mean, because it's dimension. Right? Dimension of vector space. So this is true if and only if P is inside the intersection. Make sense? Okay. It will be more than 1. Depend on the vector space you get. But if there's a point inside this intersection, it will trigger this intersection point. Okay, at least one. Okay, let's see how to prove this. So if and only if right, got two directions. So let's do the forward direction first. So forward, how we're gonna do is we're gonna do contra positive. Okay, so let's say if K is not in C intersect C prime, then what could happen? Then either P is not in one of them, maybe that's C, and then K is not an element in C, and F is then a unit in local ring. Okay, because it's not a zero set of C, or P is not in C prime, then in this case here, G will be a unit. It's not a zero set, not living in a zero set of G. Okay, then what could happen here? So either case happen because you put a unit there, right? Then you will retrieve the whole ring. Okay, you will retrieve your whole ring. Then what's the quotient then? Huh? What's your quotient? What's your quotient? You quotient out everything. What do you get? What's this quotient? You quotient everything. What do you get? Huh? Zero? What do you get here? You only get 1 point, right? Okay, so this dimension is 0. Okay. What is the thing that with dimension 1 here? If you get the field back, okay, you get 0. Any question? Any question so far? Any question? Any question so far? No? Okay. Okay, next. How about the other direction? So let's do the other direction. So if P in C intersects C prime, what does this mean? Then F and G evaluate at P will be 0. Okay. But then in this case, F and G will live inside the maximal ideal that define this P here. Okay, so if you consider the ideal generated by F and G, it's just M and P. Okay, make sense? Okay, but then what does this imply for your dimension here? So how do you compare the dimension? And dimension of OP2 quotient by MP. Greater or equal to, right? Because you are quotienting by something smaller. Okay. But MP inside this local ring is what? Is a unique maximal ideal. So after you quotient, you get a ring. Yes. Field, sorry. Field, yes. Okay. So this dimension is 1. Okay. So greater or equal to. Okay, so far. So far, okay now. So if you got a ring mod out by a maximal ideal, you will get a field. Okay. Next lemma. Okay, after this lemma, we'll take a break. Wait, let me see. Yeah, let's take a break after this lemma. Okay, so this lemma says that if you have a line, okay, intersect with a curve is greater or equal to 2, if and only if this line live inside the tangent space of C at P. Does this sound familiar? Do you remember last time I proved something about line, how when line live in the tangent space? Do you remember? L is a line, yeah. L is a line. So still remember or not? Last time I proved a statement about when is a line living inside a tangent space. Remember I draw something like this. There's also a number 2. Oh, there's no number 2 there, but we talk about multiple roots. When that's how we draw this dome here, right? That's why we draw it like this, right? There's a multiple root. So what has a multiple root? What's this thing here? Yes, okay, so you have a defining polynomial for your C, right? So if you restrict your C to this line here, it has a multiple root at this point. Okay, multiple root meaning let's say this is P, so you have a x minus P to the sum thing that greater than equals to 2. Okay, and then plus sum H, your F, restrict to L. Okay. So now we're gonna translate to here also, then greater or equal to 2 also. Okay, so how do we relate the power to this intersection number here? Okay, so let's recall the thing that we proved last time. So recall that K is a multiple root of F restricted to L if and only if L live inside the tangent space of C. So then how do we relate these two? So it is enough to see, it suffices to show that actually IP CL is equals to the multiplicity of F restricted to L. Then the number will grow like the multiplicity you want. Okay, greater or equals to 2. Okay, so how to do this? Well, a bit tricky here. So let me write it down. So to see this, first, we're going to move our P to a nice place to make argument. So we can make a linear transformation here, or maybe projective linear transformation. This is the thing that we didn't touch much. But can you believe me that I can swap P to this point? It's like in an affine case, right? How do you swap point to the origin? You can take translation. Okay, so there's a translation version in the projective space. And then L is given by, let's say, x1 equals to 0. Okay, so that there's an intersection here, right? So L is really intersected and P. Okay. Well, so in this case here, we will look at, let's look at, yeah. So then we can look at some chart. Okay, so which chart you think I need to see? Which chart is convenient here? What do you think? I make it 0, 0, 1. Or what do I mean here? This point will live in which chart? Okay, what do I mean by chart here? So which open set, the standard affine covering, which standard affine covering that this P live on? 0, 0, 1. Which pi is non-zero? Huh? U2. Okay, I live in U2 here. So in this U2, right, we have this affine coordinates. Let's make it x0 over x2 and x1 over x2. Okay, so this is the chart or the standard affine covering we're gonna use. Why are we using chart here? Because it's like differential geometry also use chart. But anyway. Okay, so if I look at this chart, what happened here? So this is the place where x2 is non-zero. Then the line L intersect A2K becomes what? will becomes this y equals 0 line here. Okay, in this standard affine fabric, because s1 equals 0, right? We make s1 equals 0. Okay, so this one make y equals 0. Okay, so now we're going to calculate in this language here. So we have IP of CL here is equals to the dimension E2K, okay, over F and X1. Okay, this is in the projective case, but we're gonna put it inside the affine case to compute it. Okay, but what's this? Okay, just now I put it in the chart S2 equals to 1, right? Not 0. Okay, I substitute as 1. And then I QY. What's left inside here? What's left inside here? What's left inside here? FX, right? Y becomes 0 already. Oh. And then the third coordinate I also substituted already. So everything inside there is just fx. Okay, so you take a ring mod out by some fx. Okay, then what's the dimension there? What's the dimension there? Sorry? No, my question is just what's this dimension? After taking y equals to, what's the dimension of this portion? You have a ring portion out by fx. What's your basis? Huh? Degree of n, right? Yeah, degree of n. Yes, exactly. Degree of f. Yeah, degree of f plus 1. 3 plus 1. Why do you need a plus 1? Let's say you quotient by Sn. What's the basis? 1 to x n minus 1, right? Because you q Sn already. Okay, so basically this is equal to the multiplicity of f at p. Okay, so we can write it as a product of okay. Any question? Any question? Okay, let's take a break. Let's break until 5:19. 至于这么以前就没有在啊？啊？什么国家？哦啊，噔噔
还真有跟 blow up 有关的东西。
什么东西？
我说这里还真有跟 blow up 有关的东西。
跟什么东西有关？
blow，
对啊，对啊，对啊，对啊，对啊，对
但是我没有读懂这个句子。
对，
它是把 A two 乘以 A two 在，
他会把一个 quotient variety blow 起来。
嗯，这个 G 二只是那个就是那个 S two 的意思。
嗯，
这边这个花体的 G 二就是那个
对啊，
symmetric group S 二的意思。
对啊，对啊，
所以我们刚刚理解的是对的，其实就是 A two 乘 A two 在 quotient 掉一个。
但是还是不明白那个 map 是什么，我是不明白的。
他这边给了这个 map，然后按照他的这个 map 的话，其实我们只要想的一个问题就是说，为什么这个 multi xz 只在两个点有取值，
那怎么点有曲子？
只在两个 x 地方有取值？因为你看它这个地方定义成为 x in a two 的这个 formula，
不是这个 x，这个 x 怎么会是个 zero of 一个 ideal 在那个世界？
你看 zero，
就是这个 z 啊，这个 x 怎么是这个 z 的 zero？
这个 x 为什么是在路？
对，这个 x 这个 zero 怎么可以写成这个 x 的形式？
我跟 0可以。
就是你拿一个 z 嘛，
嗯
拿一个 z，
，z 应该是个 idea，
啊哈，啊不是 z 应该只是一个 polynomial 吧
不是 z 是个 idea，
？z 是个 idea，
它是个 idea，
那么的话不是更神奇啊？什么叫做 multiplicity of 个 idea？
在这个点的。
我没有定义过，我只有定义过 那个 multiplicity of 个 function，没有定义过 idea 的 multiplicity 是什么？可能你去找看有没有这样的东西。这样的话，ideal 过后，这样它 defining 的
这
point
就下
make
面写的是
sense
multiplicity of the point。
of 那个 point。
嗯，
那什么叫做 multiplicity of 那个 point 在那个 ideal 上面呢？没有定义过，
好问题。
我没有定义过 multiplicity of 一个 ideal。但问题是 zero set of 这个 ideal 怎么会是长成两个 double 呢？不是很奇怪。
因为应该是这整个 sigma 会长成一个两个 tuple，
整个 sigma 是两个 double。
因为这个 sigma 这边 x in A2 的话，应该有 infinity 一个 multi x c 的 sum。
嗯，
哎，如果只是 tuple，为什么前面会乘东西？好奇怪。我
谈东西只是一个 scalar 吧，但是就是
嗯，
x 本身我就不知道为什么它活在那个 sim 里面。
可是我
x 本身活在 sim 那个我不明白。
什么 x 本身活的 sim，
x 上 x 怎么会活在那个 sim symmetry product？
超 GPT 吧？哎，为什么？
啊？谁？我可能压力比较大。Hello, hello, testing. Okay, let's continue. Okay, let's continue. Before we reaching the Zeus theorem, right? So there's some very interesting property about intersection multiplicity here. So first, we'll define two curves to intersect transversally. I think this should be the universal definition. So what does it mean by a two curve intersect transversally? Point P, C intersect C prime. If, first of all, C and C prime are both smooth, P and the tangent line should be distinct. So what do we mean by distinct here? What do we mean by distinct here? Okay, this means that I think this could generalize to a larger space also. The tangent space of C and the tangent space of C prime should just intersect at one point, which is P. Okay, so this means this is what it means by 2 points, two curves to intersect transversely. Okay. Okay, so you can see that this intersect transversely, right? Yeah, because if you look at the tangent space, actually it's the same line. Okay, imagine this line straight. So these two lines should intersect only at one. Okay, so these two curves intersect transversely. Okay, so actually, this intersection multiplicity here also detect this property here. So lemma, two curve here, C and C prime, intersect transversely at P, if and only if IPCC prime is equal to. Okay. By the way, Saya, this one very is the thing that we look at in the paper intersection formula. This is a simple version. The one we consider in my paper was graded intersection number. Okay, so there's a grading for those now. But here only simple one. Just count how many. Okay, so how to prove this? How to prove this? It's also a very interesting proof, so I think we should go through. So again, we could assume P is actually 0, 0, 1 also. Okay, and we also work with affine coordinate x1. Okay, so doing some appropriate transformation. Okay, so consider. So almost is like 0, 0, 1 is my origin in my projective space. All right. Yeah. What? Work with. Work with. Okay. So since which direction we're gonna do first? Eh, ooh, uh, uh, let's do the backward first. Okay. So since we know that P is in the intersection, okay, from what we discussed before, right? F and G will lie inside the maximal ideal defined at P, right? Because both of them disappear, right? I mean, get killed at P. And IP, which is of C prime is equal to 1. This two line implies what? Just now we already see, right? Just now we see, right? What does this imply? Your local ring portion out by this ideal here is equals to 1. But this just says that this ideal here is as big as the maximum ideal. Okay. Okay, just now, let me question you a bit. So do you know why only multiplicity of F at P matters? How about the rest? Let's say you can pull out X minus P, but how about the rest? Maybe X minus something else like Q. How about the rest here? What happened? Huh? Sorry? These are non-zero, right? But these are actually the unique inside your local ring. Okay, so we don't okay. Okay. This. So just now, this is equivalent as saying that this ideal is just as big as your maximum ideal, right? So 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 what? So how? we want to show that two curves intersect transversely. How to show two curves intersect transversely? We need to show that two tangent lines are distinct. How to show that two tangent lines are distinct? You need to show that the two lines actually somewhat linearly. I mean, their corresponding function should be linearly independent from each other, so that the two lines different. So who defined this tangent line? Who defined the tangent line? Last time we defined tangent space, right? How do we define tangent space last time? What do we call them? The partial thing. Still remember or not? The partial f. Calculus 2. Jacobian. Yeah, the coefficient will together form a Jacobian. Yes, that's the language I put into your tutorial. Yeah, so the Jacobian, yeah, the variety defined by the Jacobian. Yeah, I think you can say that. Yeah, because the Jacobian time xy, as the xi will back the equation. Actually, it's the kernel of the Jacobian, right? The kernel. Okay. So so I think I'm not writing wrong here. So if IPCC1 equals 1, then the linear part of F and G must span the two-dimensional vector space of MP over MP squared. Okay. Everyone believe this is a two-dimensional vector space. Do you believe? If you believe this, then because there are two things spanning two-dimensional vector space, right? Then this means that they have to be automatically linearly independent. Okay, so if they are linearly independent, then the zero set that satisfied should be different. Okay. Do you buy or not MP over MP squared is a two-dimensional vector space? No need to buy also can, just that I need to convince yourself why not true, why true. Not true is fine actually. To be different from other is actually fine. Maybe you might get how to say expect from the group, but that's fine. So you will find your own group in the end. 对吗，Adrian？是不是这样讲？是吧？啊，看我。Okay, never mind. But why is it two-dimensional? Hey, cannot think about this, or then we blackboard this, or can think about it or not on the spot. Why is it two-dimensional here? Hmm? Too big, I think either one or two, but well, okay, wait, first of all, this dimension here is what is equal to the dimension of your tangent space, right? Do you remember? This is isomorphic to the tangent space. Okay, at least the dual of this is isomorphic to the tangent space. But we know that the dual and its vector space is the same dimension if they are finite, right? Okay, so you can think of it as the same dimension as the tangent space. Is it two? Two-dimensional dimension of the tangent space is what? Where does MP come from? Where does MP come from? Ask yourself, where does MP come from? Where do we get this MP? This MP actually is not C prime. This MP is something correspond to the ideal of the P point at the P2. At P2, right? At P2, what's the dimension of P2? Okay, I made you prove that the dimension of Pn is n inside the tutorial. But I think it's not too hard to see that Pn should be smooth. Okay, in other words, actually all the dimension of the tangent space at every point should be the same. Okay, so it's dimension 2. Okay, so in this case here, this is the dimension of tangent space P of P2, okay, which is 2. Okay, make sense? Dimension of this guy. Okay, can understand or not? Can follow? Eric, Seng. Okay, so Pn is smooth, so we define dimension of a variety as a minimum of dimension of tangent space, right? Because it's smooth, then every dimension should be, every tangent space have the dimension of the variety. Okay, so dimension of all TP P2 is 2. And then dimension is isomorphic to MP over MB squared, the Zariski tangent space. Okay, so they have the same dimension. Okay, so far. Okay. All right. Next, how about the other direction? So now, assume conversely that C intersects C prime transversely at P. Okay, so then we work backward. No? So we look at the linear parts. So meaning look at the tangent space that's spanned by F and G. Then they should be linearly independent as well. Independent as well. But you have two linearly independent vector inside a two-dimensional space. What do you expect? Now, what do you expect? Two linearly independent vector inside a two-dimensional vector space. What do you expect? Let's say FP1 here, QP1 here. It should just equals to MP over MP squared. Okay, but last time we used the Nakayama lemma says what? If you know how to generate your quotient module here, then the same generator will generate your MP. Okay. Okay. Make sense? Okay, then what? Then you can show that IPCC prime is equals to 1. Okay. So you are quotient out a maximum idea. Okay. There's an example in the textbook. Maybe we can just quickly have a look here. We have a look. There's a nice picture there. Okay, so if you look at this parabola here, so this is a very familiar parabola like this. Okay, so we want to ask, so what's the intersection between between what? Oh, there's two things we want to intersect with this line. one line is z0 equals to 0, one is z1 equals 0. Okay, so the subtlety here, so one is like this, one is like this. Okay, intersect this curve. Apparently, this two number is a little bit different. Okay, a bit different here. Okay, so okay, from this picture, what can you see? Where do they intersect? For both these lines intersect with C, where do they intersect? 0. Okay, so we're gonna check what's the intersection multiplicity there. Okay, if we check with L1, what are we killing here? So although this one is a projective curve here, but we just look at it as a local chart. Okay, just look at a local chart here. And both our line will live inside this chart. Okay, both our line live inside this chart here. Okay, so for the first chart, the z equals 0 pi actually is a s equals 0. Okay, so at what we're saying here is this one is a projective space, but we just see it as a A2 here. Okay, so that's why this curve here, we remove Z2, Z2 equals to 1. Right, so that's why they become only two variable here. Okay, so if you quotient this, what do you get? Okay, you qx already. First of all, you qx, right? So this generator here become what? S squared minus y cube. Become just y cube. Okay, so you qx, you qy cube. What do you left? What you left with? This coordinate ring, this local ring, is generated by what? 1 x and y, right? Okay, so you q all the x already. You q y cube. So what's left? 1y and y squared. Okay, so 3 dimension 3. Okay, how about the next one? You kill y direction. Okay, y get killed. What left with this generator? S squared. So the quotient by s squared generated by what? 1 and x. Okay, so it's 2. Okay, so different way of intersection, you have a different intersection multiplicity. Okay, kind of interesting, huh? Yeah. Okay. Next theorem. Next theorem actually is a precursor. No, can I tell precursor? It's something before we prove the general statement. So let's say we have a curve degree D, okay, and a line not contained in C, like what we did just now. Okay, a line not in C. Then C will C and L intersect at D point. Okay, counted with multiplicity. So what's this D here? This D here actually come from where? This D here come from the degree of this curve here. Okay, degree of a curve. Did we define the degree of curve? Basically, this degree is referring to the degree of the defining function. Okay, yeah. Does it apply here or not? Let's see. So here is P2, right? So this is degree 3. Oh, degree 3 counted with multiplicity. So with L1, it is 3. So this one mesh up, right? But the other one is 2. Did I do something wrong? No, leh. So does it break? Jeng, jeng. How? Where the other one go? Where the other one go? The first one, okay lah, 3 match up with the degree of the polynomial because this highest is 3, right? But the other one is 2, so how? Where's the other one go? Max break already. I think the claim is there's another intersection. Remember, this is a projective space. We just look at one chart. Maybe you can go to the other chart and then you will find another intersection. And then, I mean, from here, you should guess if there exists one, where should it be? I mean, what point should it be? It should be at the point that it doesn't cover. What's the point that it doesn't cover in this chart? The infinity point at S2 equals 0. Okay. Yeah, that to you. So you should go and try and show that I think it intersects the point at infinity also. Okay? Make sense? Does it make sense? 懂我在讲什么? Because this projective curve right is not the whole picture yet. This is just some affine part. One affine part. So what's the difference there? You still have another point in that point at infinity. Okay. So this, I think this line also like they will meet up there. 懂我在讲吗? So I guess visually it's something like this. Visually, I guess. Let's say I close this line. Oh, which line? Y. So it's a vertical line. Okay. So I think they meet in the heaven. I don't know how to draw, but but I mean like, yeah. Yeah, they should be at some point in the infinity. Huh? Yeah. Your idea, man? No idea. Maybe how about draw like this, Draw like this, Okay. Then go back. Then come out. 这样把它包起来啊！讲，圆圈呀，圆圈，把它包起来呀，把它包起来。I guess. Yeah. Okay, right. Okay, man. Okay. Yeah, go and prove it. There should be another intersection point. Okay. Okay. But how to prove this? How to prove this in general? Okay, how to prove this in general? So well, also we play the linear transformation game, okay, on projective case. So we assume L to be this line here. Okay. And then f is some f equals 0. C is defined by some homogeneous polynomial. Then we'll restrict this function to this line because we want to see what's the common 0, right? Okay, after we restrict, what happened? We kill all the S2. Okay, but your function still have S0, S1 here. Okay, still have S0, S1 here. Then what happened? What we can do next? We can do a further simplification here. Okay, because L is a line. Okay, what can represent this line here? I already kill S2, right? What else you can kill? Okay, well, I mean, we can make the line contain this point. Okay, 1, 0, such that it is not a 0 on this line. Okay, so meaning we shift L such that it contains a 0 not in this line. We can do that because why we can do that? Because the intersection between two curves, right, shouldn't be infinite. Okay, so that we can do this. Okay. Then what happens here? What happened is we could then count the number of points where C and L intersect by setting S not equals to 1. Can we do that? What are we actually doing here? What are we actually doing here? So if we can do that, okay, let's say we can do that. What's left here is just degree D polynomial. Okay, so FTA says that you can find the theorem here. Okay, but why can we do this? What are we doing here? What are we really doing here? So we are trying to intersect two lines, right? C and L. Okay, and then we look at one chart. So we met x2. Sorry, we haven't looked at one chart yet, right? Ah, right, good, very good. Okay, so just now s2 equals to 0 is just a line. Okay, so we vanish at that line, and then now we just focus on one chart. Okay, so this 1 0 here actually is focusing on one affine chart. Okay, and then yeah, then substitute into it. Does it make sense? Does it make sense? Uh, yeah, maybe you can ask which line doesn't make sense. And this is like you present to me, I present to you now, right? So you can question me. When you present to me, I can question you. Huh? Scary, man? You can question me? I'm presenting now. No, no. You can question me. Sorry? Yeah, so this is a naive thinking. This is naive. This is not how you lose mark. How you lose mark is you don't try, you will lose mark. Okay, if you give up, you will lose mark. Okay. Afterward, there's a different level of answering. So compare with another person that can answer on the spot. What do you think? Yeah, obviously you can do that, but you need to understand that you are put in comparison with the rest. Yeah, so yeah, it's a different mark. So obviously you can do that. I think that's the minimum you should do actually. That's the minimum. Okay. Huh? She said that maybe answer afterward. This is the minimum you should do. Okay. If you don't do this, your mark is negative. Obviously, I won't give you negative mark, but your impression to the rest will be negative. Yeah. Hey, this is a very good scenario. It could happen, always happen one. What happen if you answer but answer it wrong? First question I ask you is, how do you know it's wrong? If you think that it's correct, then from your point of view, it's correct. If you, when is it wrong? Two cases. One is you realize yourself is wrong. Second is people point out it's wrong. So how do you react to this? So let's say the person convinced you already wrong. Okay, you go and argue. Okay, I think this is correct because blah, 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 blah. And then until he said one counter example. Oh, yeah, wrong. Okay, wrong. Yeah, right. Correct. Acknowledge the person. Okay, or apologize. Okay, just now. That's it. That's it. Nothing to do much. That's it. Yeah. Yeah, that's right. So how to convince people that your point is correct? You need to give counter example or you need to prove. This is the very first thing I always test you in my class one, in the exam. Yeah. Okay, if you fail to do that and then you only know how to do calculation, who cares? Nobody cares. Okay. Yeah. Okay, hey, come back here. Hey, you know what's going on here? You know what's going on here? Okay, first of all, I just make my life easier, make my line to be s2 equals to 0. Okay, and then I substitute it in because I need to vanish there also, right? Because intersection mark. Okay, need to satisfy the L equation. Second, what I do, I look at a specific chart. And I look at specific chart. Okay, make sense? Specific chart. Okay, because that line is in S2 equals 0, right? So obviously, then 1 0 should live inside there. I mean, after transformation actually. Okay, to make life easier also. Yeah. Okay. You cannot say I want to make 0, 0, 1 inside there. Cannot because S2 to be 0. Okay, so you cannot demand that. Okay, but you can demand 1, 0, 0 is inside there. I can swap the line. Okay. Make sense? Does it make sense? Any part that doesn't make sense, you can ask me. Yes. Oh, because the S2 already we kill it already. Yeah, S2. So okay. To be precise, maybe I should write 1, 0, 0. But we know that the third coordinate is always 0. I think this is a bit sloppy also. To be precise, if you like, I think I should write 1, 0, 0. But let me tell you, this kind of sloppiness, it could happen in a very professional paper because people will like automatically think about like, yeah, people will understand that. Okay? I don't know they are brilliant mind or not brilliant mind, but that's the thing that will happen in the professional paper. Like that. Huh? Yes, abuse of language. Yes, abuse. Mathematician like to abuse people. Okay. Anything else? Anything else? Anything else? Okay. Okay, let's reach to Bezout theorem before we call it a day. And then next week we'll do Riemann rock. Okay. Let's do Bezout. Should I write? Should I not write? Not write. Don't write. Waste time later. Okay. So Bezout theorem says what? We don't just look at a line anymore. We just look at a random plane curve. Okay, random plane curve of different degree. And then what's the intersection? Same question asked about these two lines here. Then the intersection here will be dd prime. dd prime. Okay. D times d prime here. But obviously the d times d prime here will be counted with multiplicity. It's not d times d prime distinct point. Not distinct point. It's counted with multiplicity one. Okay. So how to prove this? Let's see how to prove this. Okay, so we're gonna use divisor stuff here. We're gonna reduce to the line case. Okay, let's see how we're gonna reduce it. Okay, so suppose we have two curves. Okay, write down the two curves. Okay, defining function f and g. So f and g are homogeneous polynomial here. And by assumption, C prime does not contain C. Okay, if contained, then you could imagine that you intersect at infinitely many points, right? So we are not discussing those things, those cases. Okay, so for every point P in C, we can view the equation G of C prime as a regular function in a affine neighborhood of P. Does it make sense? Yeah, I mean like, because these functions are coming from the same ambient space, right? Okay, so we just viewed it as a regular function around P. Affine neighborhood here just says that you look at the affine standard affine covering, you pick one UI, okay, and then study there. And we can, so this means that we can view G as an element of OCP here, okay, well defined up to a multiplication by a non-zero scale. Okay. So in this way, C prime will define a divisor. Okay, so here is where we get the divisor here. So how do we get this divisor D here? Basically, we just look at what's the point that vanishes at G? Make sense, man? Does it make sense? G is the defining C, right? So you want to see what point of C can this G vanish. Natural, huh? Okay. So then VTG is just recording what's the power of the factor that you vanish. In this case here, what did you see? But ITCC prime here is equal to the multiplicity of G and C prime. You prove this? Is this what we proved just now? Is this what we proved just now? We prove it for line, huh? We prove it for line. And then, hey, this thing seems like we haven't proved it, and we just prove it for line. Let me think, Yeah, so why this is true, We only prove this for line. Why it works for this? Let's see. Thus, this is equals to the degree of P. Let me see, Okay, so if after this blackboard you can follow or not? So after this blackboard, so VPG is just multiplicity of P of G. This is okay. Okay, this is how we define VP. And then after we got this, then the sum of this intersection multiplicity is just sum of this VPG, right? But this sum is defined to be the degree of this divisor. Okay, this one okay. Okay, but how to get this? Hey, we didn't do this. I thought just now we proved this for line. Let me see. Is there something we mix up? Wait. Yeah, okay. This one we mix out. Anyone know how to fix this? Seems like I missed this. So anyone know how to fix this? Just now we prove it for line, right? Like this. Okay. This one is curve. Does it still work? We didn't prove this, or why miss this line? Is there any way to push this up? Is it clear why? Can we straight away work it out? So this is equals to the dimension of O P over Fj. Okay, and then what do we do here? What do we do here? What do we do here? K is in C, right? K is in C, meaning Fp is 0. How does it work? Fp is 0. G and C prime. G and C prime. G and C prime. G and C prime. You have to restrict to C prime because just now L also restrict to L. So, but this is coming from should this be F? I think this one should be. Oh, okay. I think I need to fix this. I need to fix this. I think something wrong. Should I use F instead? Because just now the F is coming from C, right? But here is G. I think I need to fix this. Okay. But after this, I think this is obvious. Is it obvious? Okay. I think I need to fix this. Something wrong here, I think. Because just now the F actually come from C1. Yeah. I think I need to fix this. Okay, but the rest is okay, right? Okay. So now is the job is to see why the degree of this divisor is equals to d times d prime. Okay. So if we can show that the degree of d is equal to d times d prime, then we are done. Okay. So now consider this rational function here. Basically, it's g over s naught d prime here over x naught to the d prime. And then here we assume that c is not this line here. Then the rational function here, why we pick this? Because if we consider divisor of this, it's actually d minus d prime times d naught. Okay, so d naught is the divisor divided by s naught. Okay, because there's a pole here, right? So that's why got minus d prime here, because the multiplicity here is d prime. Okay, and then G define this divisor d, right? Okay, so we still have our d here. Okay, and then we have a factor bit here. So this is the part here. Okay, so this is why we look at h. Okay, actually we want to look at this different. But what do we know here? Because this is a principal divisor, right? Okay, we prove that the degree of this principal divisor is 0. Okay, so this 0 is equal to the degree of this, but the degree of this difference actually is linear. Okay, the function degree is linear. Okay, it's a homomorphism. Okay, then you split it out. After you split out, what it says here? So degree of this d, okay, the one that we defined for g before, is actually d prime times the degree of d naught. Okay, so just now we want to show what? Degree d is equal to d times d prime, right? So if we can show that degree of d prime, d naught here is d, then we are done. Okay, so what does it mean here? What does it mean here? So to find the degree of d naught, this is defined by s naught. Okay, so basically you just look at the line defined by s naught equals 0. Then the degree of d naught is just c times l reduced to the general case. I mean, not the general, the specific case that we had just now. Okay, c times l is equal to the degree of d naught. But c times l, do we know that? Do we know that? This is the general case, right? And not the specific case, right? So d times l is just d, which is the degree of c. Okay, which is d. Okay, degree of c is d. Okay, make sense? Okay, so the specific case is quite important here. But I think I need to fix this, this one, this part here. What's really going on here? I think I messed up here, I guess. I think I messed up there, but I need to check. Okay, so this is the Bezout theorem. So. Okay, using a divisor to prove it. Okay, any question before we finish? Any question? Okay, I will fix it and then I'll let you know. Okay, see you next. No, see you Saturday. See you on Saturday. Okay.